Afternoon, everyone. Welcome to our May Decarb Lunch. My name is Mariko, and I'm the Program Manager for B2E at the Zero Emissions Innovation Center, also known as ZEBx. Today we have speakers from NRCan and Ecolighten to talk about heat pump retrofits in homes. Heat pumps are increasing in popularity, but one bad installation in a friend group can alter an entire community's perception about this energy efficient technology that both heats and cools. So the speakers will discuss the top ways that heat pump retrofits can go wrong and talk about best practices to avoid poor performing systems. And so if you have questions for the presenters, please engage in the chat. It's also a place to connect with the audience, add relevant resources, and provide comments. I'm joining you today from the traditional and unceded territories of the Musqueam, Squamish, and Tsleil-Waututh nations. We respectfully acknowledge that our staff and collaborators live and work across British Columbia and on the territories of many First Nations who have stewarded these lands and waters since time immemorial. I'd also like to thank the City of Vancouver and BC Hydro for their financial support. Their support enables us to offer these continuing education accredited webinars for free. My colleague Victoria is going to drop some details about continuing education credits for attending today's webinar into the chat. And Victoria will also launch our first poll to help us get a sense of who's in the room. Before we dive into the presenters, I just wanted to quickly share a little bit about the Building to Electrification Coalition. We're a member-driven coalition with over 260 organizations working towards electrifying space and water heating within buildings. And through our network, we strive for efficient electrification using right-sizing principles, load management strategies, to minimize grid impacts. And we also see demand response as a practical strategy to help save money and reduce excess electricity use during high power demand times. I'm also going to let you know that we just launched the BC Building Electrification Roadmap. This is a 2026 update to a roadmap that was published in 2021. It really reflects the changing political times, and it also acknowledges the progress that we've made over the last 5 years. So I encourage you to check out this roadmap and download a copy. I'm now going to introduce you to my co-host, Jana Elbrecht from Clean Energy Canada, to speak a little bit about their programming. Over to you, Jana.
Thanks, Mariko, and thanks for having us co-host this session. I'm really excited for this conversation. So yeah, as Mariko mentioned, and I'm sure everyone on this call is well aware, heat pumps are really picking up steam in BC, and the number of heat pumps has nearly doubled between 2020 and 2023. And it makes sense because heat pumps come with a lot of benefits. They can provide cooling as well as heating. They can lower emissions, lower energy usage, and for many households across BC, reduce monthly bills. And on the slide here, you'll see some of the results from modeling that we published in December on kind of quantifying the benefits of a province-wide adoption of heat pumps in BC. And we found that it would reduce annual energy bills by a collective $675 million, nearly double the number of households that have access to active cooling, and reduce annual emissions by 3.5 megatons, which is about 6% of the province's current emissions. And all of this without increasing total annual electricity demand. And yeah, many British Columbians are seeing the benefits and are taking the step of replacing their own HVAC systems. And overall, we're seeing good success across the board. And one way to test that, if you go to the next slide, Mariko, is this winter together with Summerhill, we asked all across the country, we asked Canadian heat pump owners how they were feeling about their heat pumps. And we found that 91% of respondents said they would recommend a heat pump to their neighbors and their friends. But we of course, know that these benefits only come to full fruition when a heat pump is well installed. So despite that 91% saying yes, would recommend, there is still 9% that said they wouldn't. And in this question that was slightly differently phrased, 8% that said they were somewhat or very unhappy with their heat pumps. And, as the person who went through the data, went through the open questions where we asked people to give us a little bit longer answers on why, we saw people talk about noise, about needs for maintenance. And those are typically issues with installation, right? If you get an oversized or an undersized heat pump, you might not be getting the energy or cost savings that you were promised. If you might be facing issues with noise or having an installer need to come back for maintenance. And if you have a hybrid system and you get it set at too high of a switchover point, you might be also missing out on some of those savings and unnecessarily using natural gas. So getting that right is incredibly important, both for those households directly, this 8% here, but also, as Mariko said, we're at a crucial point in this transition, and we want to get all of those people talking to their neighbors and sharing positive experiences. So I'm excited to hear from the presenters today about some of the tools that have been developed to get heat pump installations right. And before I hand it over, I'll ask Mariko to switch to the next slide to give a quick plug. So yeah, some of the findings I shared today, more detailed research results from our heat pump survey, you can all find on our website, and you can also sign up for our newsletter there. But with that, I'll hand it over to the presenters.
All right, so our first presenter today is going to be Sneha Bernard from NRCan, and she is the project lead for the local energy efficiency partnerships team. So, Sneha, you can take it away.
Thank you, Mariko, for inviting us to present and for hosting this session. We're really excited to be here today. My name is Sneha Bernard. I'm with the LEAP team, the Local Energy Efficiency Partnerships team. I'm certainly not the main event for this. I just want to do a quick introduction of the work LEAP does in the heat pump space before we hand it off to the wonderful team at Ecolighten to talk us through heat pumps gone wrong and all the ways you can fix them. So I'll talk a little bit about what LEAP is first. So like I mentioned, we're the Local Energy Efficiency Partnerships team. We're part of Natural Resources Canada. And furthermore, we're part of the ChemEd Energy family of labs. We've actually done a ton of work in BC. We supported the development and the implementation of Step Code. We work with a ton of the programs, the Clean BC programs, with BC Hydro, with Fortis BC, with Clean BC, with the wonderful folks at ZEBx. So we're no stranger to the BC market, and we take every opportunity we can to support your programs because you guys do some really great work out there and really are miles ahead of the rest of the country, I think, in advancing clean energy technologies. So LEAP tries to take all of the great research and all of the great tools that comes out of our labs, that comes out of the federal research labs, and brings it to industry. Our goal is to de-risk the adoption of new technologies and to make homes more resilient, affordable, and energy efficient in the face of all of the climate hazards that we face. If anyone has any questions about specifically resources, please drop it in the chat or reach out to us after. We're always happy to share. So I think Mariko and Jana touched on this earlier, but it should be no surprise to anyone that despite many recent advances in heat pump adoption, fossil fuels are still the primary heating source for most of BC and honestly most of the country as well. Incentive programs and grants and support for heat pumps have continued to make a compelling business case for homeowners to switch off fossil fuels and onto heat pumps. And the good news is there's many tools available now to manage those upfront costs and to manage those utility costs. So with many of the better performing cold climate heat pump systems, we know that the operating costs can be on parity with furnaces in many cases. We also know that many homeowners are getting more awareness of the carbon emissions in their home and they want to take steps to address that. So really all this to say, without really harping on this fact, is that there's a strong business case for heat pumps, and that business case is strengthened in communities where oil or propane might be the dominant fuel source. And it sounds like most of the folks in this call would already agree with that because we're here to talk about heat pumps. So in general, why are we talking about this? So we know that HVAC sales is a competitive market. If anyone has had the pleasure of getting their furnace or AC replaced recently, you know that many contractors want to come in and make a sale and get out of your house as quickly as possible. They'd like to do that, install and leave. And this is a challenging market for the heat pump space to operate in. They have limited time to provide a quote. Contractors really want to maximize that conversion to sales and sort of minimize the amount of time they're spending explaining things to you. But better quotes for heat pumps really rely on having better information, better data, and really understanding and taking the time to understand the current home conditions. That lowest cost approach may also lead to poorly performing systems. So most folks, when they're making a $10,000 or $15,000 investment in their home, would really like to take the time to understand what it is they're buying. So that lowest cost approach can also be a challenge sometimes. And this is the landscape we're operating in, and this is the landscape we're trying to embed some best practices into. What's at stake? So I think you'll hear about this in detail from the Ecolighten team, but to put it briefly, there's a lot at stake. There's, of course, unnecessary additional costs for heat pumps that might be oversized or maybe not well suited for your home. Contractors hate callbacks, programs hate callbacks, homeowners hate having to call back folks to fix things that went wrong. There's shorter component lifespans due to overcycling, due to poorly installed components, so system failures, replacements, excessive noise, higher costs, lots of things that can go wrong if your system isn't installed properly. So without thoughtful design, the likelihood increases for this potential pile of problems that we see this unfortunate contractor here struggling against. My colleague, Jeremy Leger, who's on the line, and I have spent the past few years trying to build out some best practices for the heat pump space. And we've narrowed it down to these 5 best practices that we're going to be talking about today. This is to say that this is sort of the basis of a good install. It's certainly not an extensive list of everything that has to be done, but it is the basis of what you need to get a heat pump installation right. The first is knowing your heating load. And using the CSA standard specifically to accurately gauge the heating needs of the home. So not a rule of thumb, not basing it on existing HVAC equipment size, but actually taking the time to do that calculation. The second is understanding the existing ductwork. So specifically ensuring that the ducts can provide sufficient airflow for the heat pump system that's installed. Assessing your electrical capacity and avoiding unnecessary panel upgrades. So I'll talk about this in more detail, but a heat pump retrofit or an electrification retrofit does not automatically need to mean that you get a new panel. Optimizing your control settings, you're actually getting the most use out of your heat pump and you didn't just install a glorified AC. And then finally, leveraging NRCan's air source heat pump sizing and selection app to tie together all of this information to make a decision that is the best fit for your home and is based on more than just first costs or upfront costs. So I'll talk a little bit about these in detail, and I'll go through this fairly quickly because I know we have a presentation from Ecolighten as well. But the first step is, of course, knowing your heating load. And a heat loss calculation is the first step to HVAC design that meets your home's needs. It's the basis of all the good design that follows, to know what the heating load is and to know what size of system you should put in to meet that heating load. We have a fun little game we play when we work with contractors and we run these workshops in person, where we provide some details about a home, maybe show a video of a home, provide some details about the condition and recent retrofits, and ask contractors based on that information to guess what the heating load is. And it's shocking because in some cases they're off by an order of magnitude. And if they use that rule of thumb, they would be an order of magnitude oversized for the size of the heat pump that they would install. And as we know, that can lead to a lot of challenges up front. So F280, using the F280 method is best practice, and there's a ton of tools available, which we'll talk about shortly, that supports that calculation, reduce the admin costs, reduce the time related to that calculation. So no rule of thumb using F280 standard. Understanding existing ductwork. So airflow impacts the size and performance of heat pumps. Centrally ducted heat pumps need higher airflow than furnaces due to lower temperature. And you need to make sure that the ducts in your home can handle that level of airflow. Otherwise, you get that noisy vacuum cleaner sensation, which I don't think many folks want when they install a new heat pump system. Measuring airflow, again, is best practice. So not relying on that rule of thumb estimate and using new standards, so the CSA C750 standard specifically, to accurately measure that airflow and make sure that the ducts can handle the airflow for the size of heat pump system that you can put in. The third is assessing your electrical capacity. So this has been a cross-country issue, and I think BC is actually very well positioned to address this because your technical safety authority has approved the use of demonstrated load to avoid some of these situations. But really the point I want to get across here is that an electrification upgrade does not automatically require a new electrical panel. Most homes, I won't say most homes, but when we've looked at a subset of homes, many of them used 30% of their 100 amp panel capacity. And there's plenty of space for a heat pump and any associated backup electrical heat you might need without switching to that 200 amp panel. The sort of default upgrades that we see across the country really have some severe implications for homeowner costs, because it's a $5,000 to $10,000 cost for that panel upgrade. There's utility costs, there's grid implications, so lots of things, and there's certainly tools available to avoid that. I don't know if folks are able to scan the QR code off here, but if you are interested, our team has developed a new tool called LeapSpark that can allow you to upload your own interval data. So you can access that from BC Hydro through your customer portal. You can upload that directly into this tool, and it tells you in the last 12 months what your panel capacity is. It's a really neat tool. There's a standardized output form that you can use with your electrical contractor that you can showcase with your mechanical contractor as well to demonstrate that you don't actually need to default to that panel upgrade. So if anyone is interested, take a look. It's a neat exercise if you're interested in your own home's performance. Finally, optimizing control settings. So this can certainly be a much more in-depth discussion that I won't get into. But what I want to highlight here is that the default settings in many cases for your thermostat and for your heat pump are not optimized for your home and for your comfort needs. There's several different strategies, and programs may have their own specific requirements, but there are ways to optimize what that control setting looks like for your home so that you're getting the best use out of your heat pump and you're getting back from the investment that you made with that system. So we have a couple of different scenarios here. We don't need to get into the specifics of the analysis, but I want to highlight something, that there's real impacts to costs and energy and GHG savings depending on which controls approach you pick. So you can see here, for example, that one of these approaches was the best cost performer to the tune of $200 over a year. That was a savings between the best and the worst performer. But when you look at it in terms of energy, there's quite a substantial difference between the energy performance of the lowest and the worst. And this has significant implications for programs who might be relying on heat pumps for decarbonization, for program planning. So significant changes in your energy savings from allowing that heat pump to run for the majority of the heating season versus relying on your gas backup heat. So something to keep in mind for the trades and for the programs that might be on this call. So I'll wrap up this section really quickly. All of these data points are great, and to put them into sort of a cohesive message, we have NRCan's air source heat pump sizing and selection tool. So this is a web app that's available free of charge to contractors, homeowners, energy advisors, sort of across the board. And it takes all of these things we talked about. So the sizing information, the ductwork information, your panel capacity, and it allows you to select a system that's based on your home's needs and your home's characteristics, as we talked about. And it allows you to look at the impact of different control settings on costs, on GHG savings, and all of that. So the goal here is a communication platform that works well with contractors and works well for homeowners. You can see that you're getting a system that works well for your home. It's not just what this guy has at the back of his truck and what he would like to install in your home. For those of you who might be familiar with this app is based on the air source heat pump sizing and selection Excel tool, as well as the guides that were developed. So it sort of synthesizes both of those into one handy platform. It's a lot more user-friendly, and it walks you through these steps in sort of a systematic way with some guidance and some pointers towards the right choice. So if you want to check it out, I think that would be great. Okay, so I talked a lot, and hopefully I didn't talk too fast. I just want to make sure the Ecolighten team has time for their presentation. But key takeaways, best practices, we talked about 5 of them, and Rob and Ryan will be talking a little bit about what it looks like when those best practices aren't followed and some of the things that can go wrong. There are tools available to support. So NRCan's air source heat pump sizing and selection app and LeapSpark are just a few of them that are available to support contractors, to support programs, to support homeowners in the field. And right sizing matters. To provide cost-effective quotes for your customers and minimize those risks for install and for callbacks. Next up, we are hearing from Ryan Coleman and Rob Pope, both from the Ecolighten team. So we've worked with Ecolighten for, I think, coming up on a decade at this point, and they're a really great team that does a lot, that sees a lot of this firsthand, and we're really excited to have them share about retrofits gone wrong and how to fix them.
Rob, we look like much younger fellows.
Yeah, those were the good days. Yeah.
I like the fact that guess the heat loss is moving to other places. That's
we should have patented that.
I know, it's one of our funnest games to play with. The not to be confused with also guess the air leakage. That's another fun one.
We'll have to incorporate that.
Yeah. So Rob and I are going to talk a little bit about. It's funny. It's your key takeaways look a lot like ours. A few things. Existing industry conditions. I'm going to tee this up. We did a case study for ZEBx a few months ago, looking at all electric heat pumps and dual fuel, and really kind of like trying to evaluate, some unintended consequences that can happen if you don't optimize sizing and selection. So, in terms of existing conditions, like conventional standards of practice, really, it comes down to there's not enough upfront consideration and planning around design, installation, and then documenting performance, and you end up with upset, frustrated homeowners and contractors alike. And the bottom line is like there's enough research out there in the industry that demonstrates and that basically systems are not being installed to operate to their design intent, and it has significant energy efficiency and other sort of value things that homeowners are looking for, compromises. So we know heat pumps go wrong, and unfortunately we know they go wrong much too often. And not to oversimplify, but a lot of the sort of like the key things that are happening is rule of thumb, load calculations, or sizing based on existing radiating plates happens far too often. A great phrase that Rob coined is the difference between coordinated design and coincidental design. And coincidental is the overriding sort of philosophy that typically happens within the industry. And the last one is just around like performance verification and commissioning. It's far too infrequent and usually never documented for the homeowner to inform future servicing. And like, is this thing installed to its design intent and fulfilling, equipment warranty requirements? Speaking of the homeowner, one point of emphasis we wanted to make is folks are really vulnerable, especially when it comes to heat pumps. And, it's a significant investment. It's extremely technical. And you really need kind of like two things working in a coordinated manner. And that's like informed decision-making and confidence in their decision-making by consumers, and then well-intentioned contractors that are helping them with the decision-making to help mitigate the performance risks. And, we weren't trying to oversimplify. This is the homeowner end of the contractor slide you had, Sanea. They're thinking about the simplest stuff of like, what is this? How much is it going to cost? Who can I trust? What are the right questions to ask the contractor to make sure I'm getting, what I'm investing in? Is there incentive? We love to throw around at these webinars all the jargon of coefficient of performance and SEER and HSPF and HSPF2, and they have no clue of what those things are. So they're really at the mercy of what the information they get from their contractor. And the bottom line is like, unlike plug-in appliances, refrigerators, and lighting, which are consumer installed, professional installation is and not just any installation, is really what's required to get optimized performance. And that's proper design and installation. And that's going to give you the performance, reliability, longevity, and safety of the new system. Okay. The third kind of like leg on this stool that we wanted to talk about before we get into the case study is quality approach fundamentals. And the emphasis here is around, good process leads to good results. And you really need to take a sophisticated approach in order to identify the opportunities and potential limitations, depending on the solution of a heat pump retrofit. So, there's really four components to that. There's the pre-changeout aspect, which is, some of the things that Sanea was talking about earlier, understanding existing systems and how the homeowner's been operating in that and what their perception of that system is, what the existing home performance is and how that influences sizing or future upgrades. I think Sanea mentioned that a lot of the conversation happens at the kitchen table. You're right. And contractors need to spend more time in the mechanical room, actually looking and reviewing the system and how the existing system performs to inform what they're going to recommend to the homeowner to invest in. And then it comes down to like actually doing calculations. And so there's load calculations, balance point calculations, tools, the great tools that the NRCan LEAP team have developed. All those things are really helpful for contractors to inform decision making and build confidence in the selection criteria of the homeowner. And then the last two, not to be overlooked, obviously, are like installation. And so, yeah, you may be buying a heat pump, but it's as much about the components around the heat pump that's going to like deliver the optimized performance as it is the actual equipment itself. So when we talk about that, we're talking about things like matched equipment, ducting enhancements, proper filtration, matched controls. And even if you get matched controls, you don't always get them wired correctly. And so you lose the entire benefit of making that investment. So the installation really, really matters. And then, we talked earlier about the commissioning side of things, and that's the performance verification and the actual education of a homeowner. We're doing some QA for Enbridge and gas and IESO in Ontario right now. And we've seen some fascinating stuff. They were at their baseline. They haven't really been doing much QA. We homeowner just invested in a dual fuel system, and they've been running the system on auxiliary the entire winter. So they basically had just been running their gas furnace for the entire time instead of actually running their heat pump. And they had no idea because their contractor didn't like talk to them when they had actually configured the thermostat and set up the system itself. So it happens, and it happens often, too frequently. Yeah, so we're gonna, our case study sort of like looked at the modeling and did some analysis on, energy savings and GHG reductions, and it's really around the sort of like pre-changeout calculation piece. But so that's today's focus. But we wanted to make sure that we included this because like heat pumps still go wrong, even if you size it and calculate it correctly, and then you do a real crappy install and not commission it. So it's really all these things need to be working in a coordinated fashion for you to get the most out of your investment and have, happy homeowners and then, good contractors. Okay, so let's get into the case study itself. And so this was just to reinforce the great slides and presentation that Sanea made. There's really kind of like three fundamentals that folks and contractors need to be looking at to inform proper heat pump sizing and selection. And that includes the load calculations, obviously, and making sure that those are like F28012 compliant and not like manual J or cool calc, but using the actual Canadian methodology that's in the standard that is with verified software tools. Evaluating existing ductwork at a minimum, like understanding the static pressures of the system, but like getting actual measured airflow is best practice. And I think we'll see more and more of that as people start to become more sophisticated. Now there's a CSA standard. There's EAs out there with, we're not the only firm now with a flow grid, which is kind of cool to see. And the third piece being around the electrical, understanding electrical service and capacity. And if you haven't checked out the Spark tool, I would highly encourage people to check it out. We've started to implement it into the low income or income qualifying energy conservation assistance program as being the default methodology demonstrated load for when doing electrical evaluations to determine whether enabling work is needed. Because what we found was electrical contractors were typically going to the traditional load, and that's much more conservative. I think you guys have done a webinar on this. So what we wanted to do is like, look, there's a tool, there's a way of doing this, and we'd much rather be investing in heat pumps which save energy than having to do a whole bunch of unsaving enabling work through panel and service upgrades. So yeah, the Spark tool is got some legs for sure. Yeah, I guess the last point of emphasis here before we get into the actual case study is like, each one of these components is critical, and you need this data in order to be able to use the super cool tool that NRCan has developed to be able to do heat pump comparisons and check apples to apples and look at what the different costs are, energy savings, GHG reductions, all that kind of good stuff that comes from the mobile app that they've developed. Okay, I'm going to hand it over here to Rob here in a second. So this is our case study house. It is a typical kind of home, built in 1982. It's a single-family detached house, 2-story in Kamloops, 2,500 square feet, mid-efficiency gas furnace, 60,000 BTUs input, and it's centrally ducted. And so we're going to pretend that we've gone out into the field and we've collected some data. And so we know now that the design heat loss for the house here is 41,000 BTUs. We know that the cooling load is about half of that, so it's typical. The measured airflow from the system was 815 CFM, and we know that from that, doing some extrapolation using the fan laws, the maximum airflow for the ductwork is around 1,000 CFM. And then the panel, we're going to play it simple here. It's got 200 amps. It's got 100 amps available, so we should be able to do what we need to do with both electric and gas solution. And so in the sake of time, we didn't want to dabble into any further into that. So what do we know? So we know that the home's going to need 40. So keep these numbers in mind. We know that it's going to need 42,000 BTUs of heating, and the design condition in Kamloops is minus 23. We know that the ductwork has a capacity for 2 to 2.5 tons of heating, and we know that as we said, the electrical is not an issue because we have available capacity and breaker space on the panel. So now I'll turn it over to my friend Rob, and we're going to do 4 different scenarios. So we're just going to walk you through. We've got a all electric scenario, which is a conventional, like kind of a more conventional electric heat pump with electric supplemental compared to a cold climate heat pump. And then we've got a dual fuel system with different sizing of heat pump, like a traditional method around sizing for cooling or prescriptive temperatures within the market, and then one that is like fully optimized because we know what the heat loss and we know what the ductwork can handle. Mr. Pope.
Thanks, Ryan. Okay, well, let's start. We've got 4 cases really in 2 general categories: all electric and hybrid. And I want to say from our experience, what is the most common approach to equipment selection or system type selection is the HVAC contractor will basically tell you what the best system is without options, without doing any cost benefit analysis, without giving you some idea of the upside downside for various options, which is what we're hoping to do now, is demonstrate the benefit of doing various options. So here we've got 2 in the category of all electric. One is an air handler with a heat pump, but a conventional heat pump sized for 2.5 tons. It has a heat and season performance factor 7.8. In this case, we're going to use 15 kilowatts of auxiliary heat. That's 15 kilowatts electric resistance auxiliary heat. Next to that, we have a separate option in the all electric category. It's identical with the exception is we're using a cold climate heat pump instead of a conventional heat pump, which in my opinion has revolutionized the applicability of heat pumps in our Canadian climate. This system is sized for 2.5 tons, but its heating season performance factor goes up quite a bit to 9.0 from 7.8. The supplementary heating or auxiliary heating actually goes down to 10 kilowatts of electric resistance instead of 15 kilowatts. Now let's see how that works. This is a balance point calculation. This is an equipment selection tool. It tells you the capacity based on the equipment's performance curves at outside temperatures, what it'll be able to do at your design condition. This is really critical. Every single brand out there and the models within those brands have all different performance curves. And so you really need to, once you've determined what kind of equipment you'd like to have, is check into it, plot its performance curves against the heat loss and design conditions, and this is what you'll get. In this case here, we're looking at the first of those two all-electric options. The 2.5-ton heat pump will manage 100% of the heating load to an outdoor temperature of -2 Celsius. The supplementing heating is sized to 15 kilowatts. You can see that whole green area. That's all supplemental heating. The heat pump retrofit models 60% energy savings and 97% greenhouse emissions reductions against the base case. And I should mention, you see that little red circle there. That is the balance point. That's the point beyond which your heat pump can no longer keep up. So if we go to the next slide, we'll see a big difference.
Yeah, and I would just add, like, this is one of the cool things about NRCan's app is you can map multiple different equipment types on there to be able to do real demonstrated comparisons, and so there's a real benefit, for being able to do presentations on it, but also for contractors to be able to compare different solutions to homeowners when they're in the house. Sorry, Rob. So it's the same table, but it's the two different heat pumps. And now we'll talk about the cold climate one.
Yeah, so now you can see that we've gone to the cold climate heat pump, and what's happened is that red circle's moved. It's moved to the left. And it's still a 2.5-ton heat pump, and it'll do 100% of the load now to a temperature of -10, -10 Celsius. The supplemental heating is, as I said before, instead of 15, it's 10 kilowatts when the outdoor temperature goes below the balance point. The heat pump retrofit models 73% energy savings. That's significant, and 98% greenhouse gas emission reductions from the base case. You can see here, it's pretty visual. That little green space has gotten a lot smaller, hasn't it? That's a lot less auxiliary heat you need. You're going to be operating on a more efficient heat pump for more of the time with this approach here. And of course, this is something you can show the clients because it's visual. It's very, it's not language that the homeowner somehow has to remember and organize in their brain and understand and all that. This is very, very helpful to show them the options and the results from the options. So we go to the next slide, please. Here we go. Okay. Well, other than showing what it looks like, let's look at let's just reinforce what we said about the savings. With the all-electric, with the conventional heat pump, we're looking at 97% reduction, is that 97? It's pretty small.
Yeah, 97.
And 60% energy consumption, right? Which is really good. On the other hand, just right beside it is just go to the cold climate heat pump. And we increase to 98%. It's not much, but it's better, over the life cycle of the equipment, especially. And we go from 60% to 73% energy savings. Now, this is a real number that, kind of hits the pocketbook of your client, and so has a very persuasive element to it when making their decision. Now let's look at dual fuel or hybrid. So we modeled a hybrid system here with 1.5-ton heat pump with a heating season performance factor of 9.0 and condensing gas furnace with a 60,000 BTU capacity, 96% efficient FUE. The dual fuel alternate option is a cold climate heat pump like the first one. However, this one is a 2.5-ton with a similar heating season performance factor of 9.0, same size furnace, the identical furnace. One of the difference between these two options and why 1.5 was modeled was to hit that target of, what was it, 1 degree, Ryan?
Yeah, well, it was to like look at conventional practice, which is kind of trying to size it to cooling, and look at some of the prescriptive switchover temperatures that have been used in programs in various programs in BC. And so we wanted to like look at, okay, what is the savings difference if you like really optimize it versus you do conventional practice?
Right, yeah, and you'll see what happens, how much gets left on the table when we do that. So if we go to the next slide, same thing, balance point calculations. The first one is the option on the left that we talked about with 1.5 ton. It'll go to 1 degree Celsius. The auxiliary heat or supplemental heat, those terms are interchangeable, is using a 2-stage high-efficient gas furnace with a switchover temperature from a design point of view of 1 degree to manage the full heating mode down to -23. The heat pump retrofit model or models 50% energy savings and 63% greenhouse gas emissions against the base case. Now let's see what happens when we measure that against the 2.5 ton cold climate. And you can see we've moved to the left again. We've moved up that heat loss curve as well. So now that 2.5 ton cold climate heat pump, remember, both of these are identical with just one difference, and that is the size of the heat pump, the capacity from 1.5 to 2.5 tons. And with the 2.5 tons, now we can go down to -10 Celsius. The auxiliary heat uses the same furnace, 2-stage gas furnace. It'll have to switch over at -10 from a design point of view to manage the full load. It models a 69% energy savings and a 92% greenhouse gas emission reduction. And let's have a look at that in the next slide here. Looking at them side by side, remember one is 1.5 ton, the other is 2.5 ton, otherwise they're identical. The greenhouse gas emission on 1.5 ton is 63%, and the heating energy consumption is 50%. These are reductions, right? Savings. On the other hand, the 2.5 ton climate, that's just going up one size. And from an upfront cost perspective, that's an extremely incremental, small difference in your overall cost of installation. And guess what we get out of it? We get a 92% savings, a reduction on the greenhouse gas emissions, and we have 69% energy consumption reduction. So you can see it's a substantial difference between the two. If we measure these against the all-electric, if you wouldn't mind, Ryan, we go back to the all-electric version of those two slides there. We can see here that the difference is actually quite minimal, right? In the all-electric conventional heat pump versus the cold climate heat pump, we get a better outcome on the cold climate all-electric versus the hybrid. So this is what our point is. Way I look at it is like this. When we've done this so many times, I can't count, where we've gone and, assessed situations where something's not going right. And the actual installation practice errors, the pilot error of the installation can be fixed. Sometimes there are warranty issues. Sometimes, just straighten out that heat pump, get it level, or fix those line sets, or configure the controls properly. Those are all very fixable things if you can find the defects in the first place, right? But when you go to a place and the performance is related to the initial upfront part, the actual load calculations not being done at all or not being done correctly, and the equipment selection process not being thoroughly thought out, not checking out the balance points. Also, not aligning the expectations of the client with the options that are available to them. based on their budget, as long as they're well informed, let them make the decisions. As long as they have the options, they have something to choose from, as opposed to, and we see it all the time. Ironically, I was in Kamloops this week to do some stuff and some talks, and the person I was staying with is going through the process of getting his heat pump changed, and he effectively got 4 quotes. They told him what he needed. There was no options, and he was, reached out to me and to ask to help him straighten it out, because the prices were all over place. The ideas were all different, and there was no explanation behind them, and there was the sets of options that were presented to him were just one per HVAC contractor. That's the issue. That's when we can't just go to the supplier and get a new part and fix it. When that part of the process isn't right, it's a big deal. It's a really big deal.
Yeah. And then I guess I would just say, one of the real meaningful things that came out of this sort of like work and fun case study we did for Zeke with NRCan tools and stuff is like all these solutions are saving really good GHG and energy. But it's amazing how much more benefit you get when you actually optimize something versus just doing it the way that you do it, right? And so I think that's the point is like, do it right and you can maximize the benefits for like all the parties, utility, contractor, and homeowner. All right, I know, Marika, you want us to wrap up because we want to get to questions, so don't worry, gonna wrap it up. All right, so our key learning, just like we got 3 points here, and it's going to kind of reinforce in what you were talking about. Guesstimation, no more guesstimation. It just leads to poor unintended consequence outcomes for the contractor and homeowners alike. So, do things a little bit more sophisticated, lots of tools, lots of information to do things properly at pre-change out and really inform like what are the opportunities and potential limitations with what you might be able to put into the home. Optimizing, as we were saying there earlier, that's the best way to achieve the full benefit of energy savings and greenhouse gas emissions. And so you got to know the heat loss and gain properly. You got to know the capacity of the ductwork calculated, and you got to know, the electrical service conditions and potential limitations and enabling work that might be needed. And then the last one we'd say is like, there's lots of good stuff out there for like contractors to embrace and utilize. And, the LEAP team in particular is building a fantastic portfolio of solutions, the Zeke folks with all of their info sheets and stuff like that to help contractors support homeowners with making informed decisions and building confidence in the investment they're making. And really the app is a great way to like evaluate different types of solutions and present those at the kitchen table for homeowners. And with that, we're done.
Thank you, Ryan, Rob, and Sneha for all of your presentations. We're going to get to audience questions in just a second, but I have kind of a burning one myself. So I have heard that many contractors use program prescriptive maximum temperature switchovers as like law, and that's what they use for sizing. So I'm just wondering if you can comment on this practice and if you have any thoughts on how we might change this. So we're using more optimized.
I think, yeah, there is no such thing as a universal balance point. That's the first thing to know. There's no such thing. It just isn't possible. As I said, not just brands, but models within the brands in their own product lines are all different from one another when you look at the performance curves. So they can't be all the same balance point. You need to know the balance point from a design point of view. That's an equipment critical, essential equipment selection process, right? To know whether that model is going to meet the expectation and the capacity and efficiency requirements that have been determined. The actual switchover may be different. You might use the algorithm of the actual equipment, based on time and temperature, which in my mind is the most effective way of doing it. And it might or might not be precisely what you determined in the balance point calculations to be a switchover. It might be, but it might not be. The critical thing is not to leave good energy out there in the yard doing nothing for you, is to use that as much as squeeze as much benefit and optimization as you can out of it. There's no downside to doing that. And there's no upside to arbitrarily picking a switchover point that leaves good energy on the table.
I cannot add. other than I would say, like, some of the traditional behaviors we're trying to change are like contractors sizing the cooling loads, right, with heat pumps and stuff. And so, it takes time to change to create the momentum to, like, do the things that we're trying to get them to do and really optimize the in the systems. But all the stuff that Rob said is, yeah.
I'm just curious, Naya, have you seen any examples of good programs that use different practices rather than like a maximum switchover temperature across the country?
I think a lot of programs have steered clear of making specific recommendations for what that switchover temperature is, and what we're recommending is that they work on, like Ryan and Rob said, working with the specific equipment and working with the specifics of the home. So it's a mixed bag.
I would say that, like, just because there's a maximum temperature, it doesn't mean that they're all just doing that, right? Like, there's really good contractors and savvy homeowners out there who are like asking for sizing, asking for what optimization is. It's just like we need to make that common practice instead of it being the, maybe not the most common practice.
Yeah, you're right. I don't think we should be asking of homeowners to understand heat pump sizing and get in the weeds. Right. I want to ask, you made a very strong recommendation against guesstimating, but there was a question in the chat about using natural gas bills for sizing. Would you count that under guesstimating, or do you think that is?
Do we have another webinar time, like another hour? We got Jeremy on the line. I might have
I was
to
gonna say,
Yeah. Okay. So the whole utility bill analysis piece is something that's like starting to nice, Jeremy, you're coming on camera. Good. I'm going to defer to you here in a second. But yeah, is something that's picking up steam as being a potential estimating method for sizing of equipment. There is some, considerations that you need to think about in terms of occupants' behavior changes and things like that. So, it has opportunity, but it needs to be kind of like managed in how we get there. How's that, Jeremy?
I think that's pretty accurate. We've been doing some research in that area, supporting the CSA F3D committee that's looking into changes around this. And I would say that it's not every case. You'll never get every case. There's always a homeowner goes away for vacation in January and it throws all the data off. Those types of cases are hard to incorporate into models. But there's definitely ways that you can do this with gas data.
Yeah, but you really do need to know what you're doing. It's not for everybody. Yeah, I mean you have to know how to analyze the data and distinguish, different times of year, know when there's heating, cooling involved, and all that kind of stuff. And yeah, there's more to it.
It's not as simple as just
coming on.
Yeah, it's not as simple as just looking at the total energy bill over the year and then dividing that by the heating degree days. If that was the question, it's much more nuanced than that in the modeling approach and how to reject bad cases versus good cases.
Yeah, and I get it. Like, people are trying to come up with like new methodologies and ways to make it easier for folks to get proper sizing, and like that's awesome. Like that, it's moving away from rule of thumb. I think we just need to be careful about how these things come to market and make sure that they're being done in a really thoughtful way.
That's great. There was another question in the chat about training. So does anyone from this group have recommendations on where people can get trained on these best practices?
Well,
question around or what kind of training?
Yeah, I mean, you're talking contractors, right?
Yeah, contractors.
Yeah, I mean, usual suspects, like,
HRAI,
HRAI.
yeah,
I think the LEAP team's doing a really good job with with the Home Performance Stakeholder Council and starting to help them with accessing the tools. They're like, I know they're working with BCIT on the micro credential and like the updated best practices guide that came out last fall that talks about this stuff. So, I mean, there's no shortage of like
yeah.
resources and tools and training if contractors want to find it and if
Yeah.
they want to embrace it.
And then there's Google.
Easy.
Yeah, and I think we have time for one more question.
Okay, there's a lot of very specific questions about technologies in here, but I think I'm going to go with a question on the hybrid setup here, or more of a comment where someone's asking about, did you factor in the economics of having to purchase two systems and run both a furnace and a heat pump versus having an electrical coil built in as backup?
Yeah, well, there's the upfront cost versus the operating cost, life cycle costs, and the total return on investment and all that kind of stuff. There's a few dynamics at work at the same time that you have to kind of put together. So yes, upfront costs. If you go to an air handler with an electric strip for auxiliary and a heat pump versus a gas furnace, you're going to pay a little bit more for the gas furnace. Probably if it's a new gas furnace, you got to run gas lines. The furnace is not cheap. You got to run the CPVC for your venting and at least PVC for your combustion air intake. And all that adds up, on your upfront costs. To do what? To save you money? It depends on the region of the country or even the region of our own province, BC. That's why, whoever's in the house at that kitchen table, as the cliche goes, I wish we would find a different cliche, that the best practice is to know what you're doing, know what you're talking about, to understand the state of the industry, the technologies available, to understand the very basic mathematics, so you can do the upside downside calculations, do some comparisons to fully inform the client in a language that they understand, and also be able to read the room, understand that client's in expectations in terms of climate footprint, whether it's economics, whether they want to geek out on the technology, whatever it is, we're all humans, and you have to be able to adjust your approach to the type of expectations and make sure they're all aligned. There's really no substitute for knowing what you're doing and learning whatever it is you need to learn to get there. And that's what it takes to take that vulnerability away from the customer and hopefully align what they need and want and expect with what they're capable of getting based on their budget and the technology and everything else that's out there.
America, I know you want to wrap up, and I would just say the short answer on that question too.
There was a short answer.
Well, no. I just want to say is like they were asking about we didn't do a cost analysis on this. It was like it wasn't. We weren't looking at capital costs and economic switchover or anything like that. This was really just looking at like what different types of systems specifically around energy and GHG. But I have nothing to add to your answer, Rob. Again.
All right. Well, thank you very much, Rob, Ryan, Sneha, Yana, for participating in this webinar. Thank you to everyone who joined us today. I have two plugs before everyone jumps off. We have a webinar launch for the Building Electrification Roadmap that I mentioned previously on May 12th at noon. And then we also have an upcoming ZEBx Tech demo at BCIT in Vancouver. The new Daikin, it's in Burnaby. The new Daikin Altherma is an air-to-water heat pump. So if you're interested in either of those, please visit the BC Green event calendar and you can register there. Thanks for joining.
Thank you. Thanks, everybody.
Bye-bye.